Convolutional neural network. Now that we understand neural networks, let's revisit the handwritten digits example.
The input images in that case were very simple, small, black and white images. Now, imagine working with a larger dataset, such as pictures of cats and dogs. A picture of a cat is obviously far more complex than a handwritten digit. Could we simply flatten all the pixels into a single array and use it as input for our neural network? Wouldn't that risk losing important spatial information? Now think about an even more complex problem: placing a camera in front of a car to detect objects in real time.
For such scenarios, a standard neural network might not be sufficient. We need to enhance our neural network to handle the complexity of these tasks. This is where the beautiful and powerful model, the convolutional neural network, CNN, comes into play. The first major difference between a traditional neural network, NN, and a CNN lies in how the input is processed. In an NN, the input is often flattened into a 1D array, which causes the network to lose all the spatial relationships and structures in the image. In a CNN, however, the input remains in its original 2D format, represented as a matrix for grayscale images or as three matrices for colored images, RGB. A sample of a colored image in the size of 3 by 3. The main picture is the combination of these three matrices. A black and white image.
As can be seen, one number is enough to represent the color of each pixel.
Now let's see how CNN works. 1. Convolution layers.
These layers apply a set of filters, kernels, to the input to extract important features such as edges, textures, shapes, or patterns. Each filter slides, convolves, over the input, performing element-wise multiplication and summation to produce feature maps. The final target is that these filters will be learned during the learning process. 2. Pooling layers. These layers reduce the spatial dimensions of the activation maps, which decreases computation and make the following process easier. Common pooling methods include max pooling, taking the maximum value, and average pooling, taking the average value.
3.
Fully connected layers. After a series of convolution, pooling operations, and some mathematic operations, the output is flattened and passed through one or more fully connected layers. This part is the same as the layers in NN, to make the final predictions.
How CNNs work.
The input, for example, an image, is passed through a stack of convolution and pooling layers.
Each layer extracts progressively complex features. For example, early layers detect edges or corners. Deeper layers identify shapes or objects. The fully connected layers use these extracted features to classify the input or make predictions.